Hello children, in this lecture we will start our discussion from order of a reaction. So this heading we have discussed already. So according to this order of reaction, the power to which the concentration term of a particular reactant in the rate law is raised. So for the order of reaction, we will require the rate law of that reaction, and this rate law is derived experimentally. That is why order of a reaction is an experimental value for the reaction. Okay, so reactant in the rate law is raised is called the order of reaction. With respect to that reactant and the sum of all the powers to which all the concentration terms in the rate law are raised to express the observed rate of reaction is called the overall order of reaction. Okay students, so for a hypothetical reaction, this reaction is given. So let the rate law for this reaction is this. Okay, so the order of this reaction in the terms of A will be P, and in the terms of B it will be Q, and in the terms of C it will be R. Okay, so the order of this reaction in the terms of different reactant will be different according to this rate law, which is obtained for this reaction experimentally. So according to this rate law, rate equals to K, A raised to the power P, B raised to the power Q, and C raised to the power R. So in the terms of concentration of A, the order of this reaction will be equals to P, and in the terms of reactant B, the order of this reaction will be Q, and in the terms of C, the order of reaction will be R. Okay students, but overall order of this reaction will be addition product of these powers, means P plus Q plus R. So this will be the overall order of reaction. Okay students, as it is written here also, the overall order of reaction. So when the overall order of reaction is 1, the reaction is said to be a first order reaction, and if the overall order is 2, the reaction is said to be second order reaction. Okay, and same way third order reaction. The order of reaction is an important characteristic of every chemical reaction. Regarding the order of reaction, following points must be noted carefully. And according to this first point, the order of a reaction is purely an experimental quantity and cannot be known just by the stoichiometry of the balanced equation of the reaction. Okay students, it has to be obtained experimentally by determining the rate law. So always to find out order of a particular reaction, we will be required rate law of that reaction, and rate law is always written in the terms of reactant, and this rate law derived through experiments. So order of reaction also experimental value for the reaction. Second point, the order of a reaction is usually a whole number, but the order of reaction can be 0 or fractional value also. Okay, then as you can see here, for this reaction the overall order of reaction is 3. Okay, then next point, So according to this example number 4.7, find out the order of the following reactions. So the reaction is given this, and this is the rate law for this reaction. So as you can see in this rate law, the reactant terms is written with power 2. So the overall order of reaction will be 2. Okay students, overall order of reaction will be 2. For this reaction, second reaction, the rate law is this. So overall order of this reaction will be 1. Okay, for this reaction, the rate law is this. So order of reaction will be 2 plus 1 by 2. Okay students, means equals to 5 by 2. So for this reaction, order of reaction is a fractional value. Okay students, the next heading is classification of reactions on the basis of order of reaction and units of the rate constant on the basis of order of reaction. So the first is first order reactions. These are the reactions in which rate of the reaction is depend upon the only one concentration. So for example, if this is a hypothetical reaction, A products, and rate law is this. Okay, rate law is this. It means the order of reaction is 1 for this reaction. Okay. Now, if more than one reactant are taking part in the reaction, more than one reactant are there in the reaction, then in that case, suppose A plus B are forming product C, but according to rate law, rate equals to K A raised to the power 0 and B raised to the power 1. So for this reaction, the order of reaction will be 1. Okay, because for this concentration term, reactant concentration term, the power is 0. So overall the order of reaction will be 1. Okay students. Now example, for example, first decomposition of ethyl chloride. So ethyl chloride, just one reactant unit is present there. That is why order of reaction will be 1. And these are the examples here. Number of examples are given there. Then unit of order of reaction. So it will be time inverse. If time is in second, then second inverse or minute inverse or hours inverse. Okay. For a gaseous first order reaction, it will be time inverse and can be written as second inverse. Then second order reaction. So for a second order reaction, the product is raised up to power 2. Okay. And for these reactions, if the concentration of A is doubled, then the rate increases by 4 times. Okay students. Now this for this on the basis of rate law, for this reaction order of reaction will be 2. But if the reaction is of such type which is having 2 different reactant terms and the rate law is this, then overall order of reaction will be 1 plus 1 equals to 2. Okay students. Now few examples of second order reaction. Just 2NO2 is forming 2NO plus O2. Then rate law will be K and O2 raised to the power 2. So the overall order of reaction will be 2. Okay. Now this reaction, it is having 2 reactant term. Rate law is this. So power will be added. Overall order will be 2. After this, unit of rate constant. Concentration inverse, time inverse. Okay. So if concentration in mole per liter and time in second, then mole inverse liter second inverse. This is the unit of rate constant. Then next is third order reaction. When the rate of reaction depends upon the cube of the concentration of reactants, the reaction is said to be third order. In such a case, when the concentration of reactants is double, the rate of reaction increases by 8 times. So for this reaction, the rate law is this. So overall order will be 2 plus 1, 3. Order of reaction will be 3. Examples of such type of reactions. Here, this reaction, rate law is this, 2 plus 1. Order of will be 3. Then units of rate constant. So units will be concentration raised to the power minus 2 time raised to the power minus 1. So the concentration in mole per liter. So the unit will be mole power minus 2 liter square second inverse. Okay, students. Zero order reaction is not in a syllabus. The next heading we are moving, reactions of fractional order. So such reactions which are having fractional order, for example this reaction, rate law is this, so the order of reaction will be 3 by 2. Fractional order reaction. Pseudo first order reaction. Important reactions, short notes can be asked from here. The reactions which apparently seem to be of higher order but under certain circumstances behave as first order reaction are known as pseudo first order reaction. So such reactions which are of any other higher different order but they are appearing as first order reaction are known as pseudo first order reaction. For example, a very good example is there, this one, acid catalyzed hydrolysis of ethyl acetate. So on the basis of this reaction, we can see here that two reactant terms are there. So apparently it looks like a second order reaction, but the rate law of this reaction is this. Why the rate law of this reaction is this? Only ester terms are there in rate law. Why not water is not there? Because water is present in a huge amount in the medium. Okay, so the concentration of water will not change with the reaction. It will remain about constant. So that is why it is not present here in the rate law of the reaction. So the order of the reaction will be 1. Okay, students. Same reason is for here also. Water is in huge amount. So the overall rate of reaction will depend upon this unit only. That is why rate law is this, and the order of reaction will be 1. So it will be known as pseudo order reaction. Pseudo order reaction. Okay, students. So these two reactions you can write as an example of first order reaction and also as pseudo order reaction. Okay, students. Now after this, rate equation for a first order reaction, and this derivation is in your syllabus. Integrated equation, rate equation. So this derivation is there. You have to do the practice of this derivation. Okay, and the final relation of the this first order reaction will be this. So this is the rate equation for the first order reaction. Important relation, numericals based on first order reaction are in your syllabus only. So you will use for those numerical this first order rate equation. Okay, so in this equation, this A naught is initial compound, A naught is initial compound, and A is A naught, and A is the compound which remains after a time period T. Okay, initial compound and the remaining amount of the initial amount after time T, which is written here. Okay, students, and this we can write, this relation we can write in this way also. So here again A is initial amount of the reactant and A minus X. This X part is converted in the form of product. So the remaining part of the reactant will be A minus X after time T. Okay, so this relation we will use. So derivation of this first order reaction and this relation. So relations are very important because all the numericals which are in your syllabus are based on first order rate reaction only. Okay, so then half-life of a first order reaction. This derivation is also in your syllabus. Half-life of first order reaction, and the final value of the relation is this. The half-life of first order reaction is T half, and this T half equals to 0.693 upon K. K is rate constant here. K is rate constant. Okay, students. So numericals from here also very important. Okay, students. So half-life of first order reaction depends only upon the rate constant of the reaction, and it is independent of the initial concentration. Okay, then next value is that amount of reactant left after n half-lives. And for this we will use this relation. Amount of reactant left after n half-lives will be A initial amount of the reactant, and 2 to the power n, where n is the number of half-lives. Okay, so by using this relation we can calculate amount of reactant after n number of half-lives. Okay, this example, a typical example is given here. So according to this example, a first order reaction is 75% complete in 60 minutes. Find the half-life of this reaction. Okay, half-life of this reaction. So 75%. So let the initial amount of the reactant is 100. 75% completed. It means the remaining amount after 60 minutes will be 25. After 60 minutes will be 25. Okay, students. So if we will take initial amount as 100, 75% completed means 75% of the reactant part is changed in the form of product. So how much amount of reactant is left in that condition? It will be 25% or 25 part of 100. So we will write these values here in this relation. K equals to 2.303 T log 10 A naught A initial upon A after time T. Okay, so with the help of this relation we will calculate first K, and this value of K we will use in this relation to find out half-life period of the reaction. So according to this relation, initial amount is we taken 100, left amount after 60 minutes 25. So the relation will be K will be equals to 2.303 upon 60 log base 10 100 upon 25. So value of K will be 0.0231 per minute, and this value we will use here. Okay, after using this value, T half will be 30 minutes. So these are the typical examples. Such type of examples are very important, which are based on the rate equation of first order reaction and its half-life. Okay, students, so you have to practice for your board examination of such type of numerical. Okay, then characteristics of a first order reaction. Characteristic. So there are number of characteristics. Few important are as the rate of first order reaction is directly proportional to the concentration of the reactant. When the concentration is doubled, the rate will also double. Then second point, the rate constant of a first order reaction has the units of time inverse, means the units of K are per second or per minute or per hour. The first order reaction obeys the following relation. Then sixth point, or before that fifth point, The half-life of a first order reaction is independent of the initial concentration. It depends only upon the value of rate constant K of the reaction. Okay, so this is the relation of half-life. And the sixth point, which is very important, the time taken for a completion of any fraction of a first order reaction is independent of initial concentration. As you can see in this relation, we are not using initial concentration. Initial concentration, this can be shown as follows for the first order reaction. So the first order, the time taken for the completion of any first order reaction is independent of the initial concentration. Okay, so as you can see here, with the help of this relation, indicates that time taken for completion of nth order fraction is independent of concentration, as the equation does not involve any concentration term, A or A naught. So independent of concentration term. Okay, students. The next is exothermic and endothermic reactions. Exothermic reactions, the chemical reactions which proceed with the equation with the evolution of heat energy, are termed as exothermic. For example, these are the reactions which are evolving energy in the form of heat, exothermic reactions. Okay, the next is endothermic reactions. Endothermic reactions are the reactions which proceed with the absorption of heat energy, are called endothermic reactions. And in these reactions, energy terms are written with minus sign. Okay, students. So in such reactions, the energy and endothermic reactions mean heat is evolved, means the heat of product is more than heat of reactant. Okay, heat of product is more than heat of reactant. The next heading is activation energy. Activation energy. So activation energy may be defined as the excess energy that the reactant molecules must acquire in order to cross the energy barrier and to change into the products. Okay, students, this statement means that all the reactant molecules which are taking part in the reaction are not going to change in the form of product. Okay, all molecules of the reactant are not going to change in the form of product because they are having different amount of energy. Okay, and each reaction is having certain energy barrier. So when reactants are going to convert themselves in the product, they have to cross this particular energy barrier. And the molecules, reactant molecules, which are having such amount of energy that they can cross this energy barrier, they will able to change themselves in the form of product only. And the reactant molecules which are having less energy to cross this energy barrier, then they will remain as reactant. They are not going to convert themselves in the form of product. Okay, so if such molecules which at ordinary condition are not able to form product, they want a specific amount of energy to cross this energy barrier, and that amount of energy through which they able to cross this energy barrier is known as energy of activation or activation energy. So activation energy equals to threshold energy minus average energy possessed by reactant molecules. So average energy which that reactant molecules are having already. Okay, and threshold energy is the amount of energy which is required, minimum amount of energy which is required to cross this energy barrier. Okay, and the activation energy which is provided from outside. Okay, so the amount of energy which is provided from outside to the reactant molecules to fulfill their energy amount up to the amount of threshold energy is known as energy of activation or activation energy. Okay, students. So this is the diagrammatic illustration of activation energy and energy barrier in a reaction. Okay, students. So this amount energy, y-axis with energy, and this is the course of reaction. These are the reactant molecules and here products. This is the energy barrier. Okay, so if reactant molecules want to convert themselves in the form of product, they have to cross this energy barrier. Okay, this energy barrier, they have to cross this energy barrier, and this is the amount of activation energy. This energy will be provided from outside to the reactant molecules to cross this energy barrier. Okay, so this energy barrier is the barrier for the molecules which are having energy less than threshold energy. Okay, and in that condition such molecules are provided energy from the outside, and that amount of energy is known as energy of activation or activation energy. Okay, students. The next is activated complex or transition state. Activated complex or transition state. So according to this concept, a chemical reaction involves the breaking of old bonds and the formation of new bonds. The breaking of bonds involves absorption of energy, while during the formation of bonds, energy is released. So when two molecules having necessary energy of activation approach each other, they attain an intermediate configuration before they change into products. This configuration possesses a higher energy as compared to the sum of the energies of reactants. The intermediate configuration corresponds to maximum potential energy of the system, and it is called as activated complex or transition state. The activated complex then changes into products and excess energy is released. So this we can represent in the with the help of this graph. Here these are the reactants. These reactants are forming an intermediate activated complex with high amount of energy, and that is why less stable, because energy of this activated complex is high, so it will be less stable, and again this compound will be converted in the form of product, and the extra amount of energy is released. Okay, so this is the course of reaction due to the formation of activated complex or transition state. Then next heading is effect of catalyst on activation energy and rate reaction. So a catalyst enhances the rate of reaction by providing an alternate path of lower activation energy, as you can see graphically here. So a normal reaction is taking place with this path. So the amount of activation energy required is this much amount, greater amount. But in the presence of catalyst, this path of the reaction from here to it changes to here. So in this condition, the amount of activation energy is going lower. Okay, and due to the decrease in activation energy, large amount of reactant molecules can take part in the reaction through this path. Okay, so greater amount of product will form, means the rate of reaction will be increased, and this is the reason why in the presence of catalyst, rate of reaction increases. Why? Because in the presence of catalyst, the path of the reaction changes from high activation energy to low energy activation energy. Okay, students. Then molecularity of a reaction. Molecularity of the reaction, only definition is there. The number of reactant species that may be atoms, ions or molecules which must collide simultaneously in the order of to bring about a chemical reaction is called the molecularity of the reaction. So on the basis of molecularity of the reaction can be of different types, as unimolecular reaction, bimolecular reaction, trimolecular reaction or tetramolecular reaction. But normally up to trimolecular reactions are common. Higher molecularity reactions are uncommon. Then next heading is molecularity of an elementary reaction. So the molecularity of an elementary reaction is equal to the number of reacting species as represented by the balanced chemical equation of the reaction. So students, one thing that elementary reactions are the reactions in which just a particular reaction is showing the formation of final product with the help of related reactants. Okay, so just single reaction is showing overall chemical change. Such reactions are known as elementary reactions. So in such reactions, the number of reactant molecules which are present are known as molecularity of the reaction. For example, in this reaction, one molecule of reactant is there, molecularity is 1. In this reaction, molecularity is 2. Then molecularity of a complex reactions. Okay, so complex reactions are those reactions which are taking place in number of steps. In number of steps, so the overall rate of a complex reaction is governed by the rate of the slowest elementary step. So if the number of steps are there, then the overall rate of reaction will be depend upon the slowest step. Okay, so as far as the slowest step completed, the reaction will also completed. So the number of reacting species taking part in the slowest step, and this slowest step is also known as rate determining step of a complex reaction is called the molecularity of the complex reaction. Okay students, molecularity of the complex reaction. So in the complex reaction, the number of reactant molecules present in rate determining step are known as molecularity of the reaction. Then difference between molecularity of a reaction and order of a reaction. Very important difference. So according to the first point, it is the number of reacting species which collide simultaneously. But order of reaction is the sum of the powers to which the concentration terms of reactants are raised in rate law expression. Second point, it can have only positive integral values as 1, 2, 3. But order of reaction can be 0, integral fraction, or can be even negative also. Then molecularity is a theoretical concept. Okay, and it is derived from the mechanism of the reaction. But order of reaction is a experimental concept and derived from the rate law of the reaction. Okay students, so today we have completed this chapter. Thank you.